Start recording. Recording start sir.
Recording.
Start recording. Start streaming. Streaming started. Okay. Ready.
അതൊന്നും ചേഞ്ച് ചെയ്താൽ മതി.
Okay. സ്റ്റാർട്ട് ചെയ്തോട്ടെ. Okay. Okay, so I think we can start. Welcome all of you to the AstroAdda of July 2022, and I am Jayant Ganguly from Regional Science Center and Planetarium, and with me we have today the speaker Dr. Preeti Kharb. So I will introduce her. She has done her BSc from Miranda House College, Delhi University in 1994, and her MSc degree from Delhi University in 1996, and her PhD from Jawaharlal Nehru University in 1997, and her PhD from Indian Institute of Astrophysics, Bangalore University in 2005. After her postdoctoral position at Rochester Institute of Technology and Purdue University in the USA, she joined the faculty of Indian Institute of Astrophysics, Bangalore, as a reader in 2012, and she has moved to NCRA in September 2016 and is currently Reader F. Reader F, no, I think Associate Professor G. There is a thing. So now her research interest is primarily related to the phenomenology of active galactic nuclei. In particular, she is interested in probing jet physics in active galactic nuclei. Some of the fundamental questions that she attempts to address in her research are: what factors are responsible for production and launching of active galactic nuclei jets, their collimations and their propagation through the interstellar and intergalactic medium, for instance the role played by the environment on jet propagation. She had attempted to address these questions with multi-scale, multi-wavelength and observational approach using ground-based telescope like VLA, very large array, and very long baseline array, and the giant meter wave radio telescope, and space-based telescopes like Hubble Space Telescope and Chandra X-ray Observatory. Her list of publication is available in her page in the NCRA TIFR website, and I think we have a very good speaker, and this is the topic actually. No, we have the image taken by Event Horizontal Telescope. First we have the image of a different black hole, and now we have our own black holes image. So people are curious to know actually how they took it and all those questions. So I think we can start. Yeah.
Thank you, Jayant. Let me just thank you also for inviting me. Let me try to share the screen now.
Yeah. You can make it full screen.
Yeah.
Yeah, fine. It's fine. You can start.
Okay, thank you. All right, so today I'm going to talk about these new exciting results that have come from the Event Horizon Telescope, or EHT for short, and what we can learn about active galactic nuclei from these observations. So I'm, of course, Jayant has already told you, at the National Center for Radio Astrophysics, and NCRA operates the Giant Meter Wave Radio Telescope. And in fact, today is the day we have released VLBI, very long baseline interferometric images with GMRT. So this talk becomes especially relevant. So let me first introduce active galactic nuclei. Okay, so what you see in this slide is two images of two spiral galaxies. And on the left, you have what is called a normal spiral galaxy, which of course shows dust lanes and all this fuzz is due to starlight. And there is an increased brightness in the center because there is an increased stellar density as you go to the center of this galaxy. But on the right, what you see is another spiral galaxy, which is also almost face on, where the fuzz is stellar light. And but in this image, what you see is a very bright point source, which is superimposed on the center of this galaxy. And this point source can be so bright that it can outshine the light from all the stars in this galaxy combined. So, so this is, now we understand this to be an active galactic nucleus, or AGN for short. And AGN can be as luminous as the luminosity from all stars in a galaxy, which is around 10 to the 11. So 100 billion stars make a typical galaxy, and the AGN brightness can be as much as that, or even 100 times more. So if you took, for example, short exposure images of this particular galaxy with this point source, you only see the point source. So a lot of the initial terminology about AGN, I mean, they were usually called quasi-stellar sources, quasi-stellar radio sources, quasi-stellar objects, because they looked star-like. As a class of objects, Carl Seifert was the one who found that there were several galaxies which seem to show this kind of phenomenon, and these are now called Seifert galaxies. I'll show in the next couple of slides. The other peculiarity of these Seifert galaxies was that when you took their spectrum, so spectrum is when you, so for example, I hope people are familiar with spectroscopic observations. So if you take a slit across the galaxy, for example a normal galaxy, the spectrum, which is basically flux density at a particular wavelength with respect to wavelength, shows lines like this. So these are known as absorption lines. So this is kind of similar to maybe the solar spectrum. If you've had a look at the solar spectrum, these absorption lines are the dark lines which show in the solar spectrum, are due to photospheres in the stars which make this galaxy. But on the other hand, when you take a spectrum of this active galaxy, you find that the emission from the center is dominated by emission lines rather than absorption lines, like here. So bright lines rather than dark lines. And these lines come from special species which are included in the gas clouds, for example, in these sources. And the species are noted here, for example, neon 5, oxygen 2, oxygen 3, H beta, etc. So these are the elements which make up the gas clouds that give rise to these emission lines. So these two became the signatures of an AGN, a star-like nucleus and an emission line spectrum. And such galaxies were then called Seifert galaxies. But it took another 20 years before radio interferometry became mainstream, that this study really caught on. And this was in 1963. Brian Schmidt found that there was one quasi-stellar object which we now know is, we now are very familiar with this source, called 3C273. 3C stands for the third Cambridge catalogue, and so this is the catalogue of radio sources, and this is the 273rd entry in that catalogue. When Schmidt looked at the spectrum of this radio source, actually, they found that it seemed to show the same lines. This is the bottom is a spectrum of gas in the lab, and on the top is a spectrum from this particular source, 3C273. And he could identify the Balmer's series of hydrogen, which you can see at the bottom here, in this particular spectra, but they were very highly redshifted. And so redshift is given by this relation, for example, the observed wavelength minus the emitted wavelength, which is in the lab frame, divided by the emitted wavelength. So which meant, so the redshift of this particular source was 0.158, which meant that this source was not in our galaxy, it was extragalactic. And now we know that this is a very bright AGN, another bright AGN, which is seen on the top panel here. This is a Hubble Space Telescope image of this source. And as as was already kind of noted earlier, it shows just a point source. But if you do some kind of sophisticated coronagraphic studies where you block this light from the point source, then you suddenly see this faint fuzz, which is the elliptical galaxy lying or hosting this nucleus. So you know that this is also an AGN. And at the bottom, this is a radio image of 3C273. And so this radio work and the redshift, optical redshift work happened at the same time. So this was happening in the US and in Australia, where the radio astronomers had found that this was a bright point source, but seemed to have another point source next to it, which happened to be this particular feature here. So as you will see also in the talk, that as and when new observational tools come about, like for example radio astronomy, and later maybe even X-ray astronomy and gamma ray astronomy, neutrino physics, etc. So every time a new observational window is opened, also gravitational waves, a new set of discoveries are made, a new set of objects are discovered. So this is just to kind of remind you that actually it was not only in the 1940s, it was much earlier that astronomers had noted some peculiar galaxies, which now we know are active galactic nuclei. So it was as far back as 1908 that EHT at the Lick Observatory had actually found that this particular nebula, they didn't know it was actually a spiral galaxy which was outside of our Milky Way. They just called it a nebula because it was like a fuzzy structure in the sky, called NGC 1068. Okay, New General Catalog. So this is another catalog of optical data. So 1068 N3 in this particular catalog seemed to show a very curious spectrum. So they had noted that. And in 1918, Heber Curtis had actually also noted this jet in this particular galaxy called M87. And M87, of course, is the topic of discussion today. And of course, that this is a much nicer image from the Hubble Space Telescope. The image that Curtis looked at was not as nice as this one, but they could still see some kind of jet. This is called a jet, collimated pencil-like feature was visible. So it was that long ago that it was already observed, but it would be many more decades before this became an object for study. So now we have a fair idea about what actually makes up an active galactic nucleus. And so this is a cartoon here to show what the central engine is, what that point source is actually. And there is a reason why this is a cartoon and not an image. And that is because at the wavelengths at which these particular components of the central engine are emitting are usually in the optical and UV radiation regime, and there are no optical or UV frequency domain or rather telescopes which work in the domain that have enough resolution, which means that they can see the details. There is no telescope like that which can actually resolve these structures. So these structures are sub-parsec scale or parsec scale, and our telescopes are don't have enough resolution to actually see this. So that's why there's a cartoon. And the cartoon has come about because of spectroscopic observations. So all the spectra contains a lot of information. So I mentioned all the species of elements which are actually in gas clouds, and these gas clouds which are moving around this central engine are the ones which give rise to the lines in the spectrum. So there are broad lines which have a certain Doppler widths, and narrow lines which have less than a few, which have few hundreds of kilometers per second Doppler widths. So all this cartoon has come about because of spectroscopic observations. And in the center, we believe that there is a supermassive black hole, and there is matter which is gas around this central black hole is falling into the black hole. And this falling into then releases all the gravitational energy, and that is launched into either these outflows, as you can see, these jets, or just a lot of high energy, high frequency photons, which you see in the optical and the UV. So this is the central engine, and then of course the gas clouds are from inferred from spectroscopic studies. This orange structure is supposed to be some kind of obscuration, which some dust and gas which hides the central engine or black hole accretion disk and these clouds from certain lines of sight for some type of AGN. So there is some obscuration also. This is also inferred indirectly, right? So let me now come to all the components of this, this model that I showed you, which now we are very sure exist. So now we know that all massive galaxies host a central supermassive black hole. We have multiple pieces of evidence which are pointing to this. And of course, the best example of a supermassive black hole comes from our own galaxy. And this is a picture of showing the parts of stars. This is captured in using infrared radiation, because there is a lot of dust in the center of our own galaxy. And so if you look at the center of our own galaxy and you look at the stellar motions in the center, which is what is being shown here. And so these are basically these ellipticals that you see are the stellar paths, stellar orbits. And they have been monitored for several decades now, so that we actually have been able to get complete orbits of these stars around in the center of our own galaxy. And so they all seem to be revolving around the central, massive object, which is dark. You can't see it in infrared light. And that is how we know that there is a supermassive black hole. So since we have both the radius of the orbit and the speeds with which these stars are moving, you can use a simple, this equation you would be very familiar with. This is the Newton's form of Kepler's third law, where you equate the gravitational force with centripetal force, and you can find what is the mass around which these stars are moving, which is v square r by g. So we have v, r, g, and then you find that they all revolving around a black hole of 4.5 10 to the 6 solar masses. So 1,000,000 times the mass of the sun is contained in this very central region, subparsec scale region. And this, you must be also aware, this work was awarded the Nobel Prize in Physics in 2020. And Reinhard Genzel and Andrea Ghez were the two observational astronomers who made these observations possible. Now, of course, we have the Event Horizon Telescope image of the black hole in the Milky Way, and so this is shown here. This is the Milky Way, as you can see in the night sky. You see the dust lanes, and this is the center here, which is also called Sagittarius A star. Sagittarius A star, of course, comes from the radio, but it's in the Sagittarius constellation, the galactic center. And here, this on the top is shown is the Event Horizon Telescope image of the black hole in the galactic center. And these telescopes are the ALMA telescopes, Atacama Large Millimeter Array, which were instrumental in getting these images. So before I go to the EHT results, I wanted to introduce a couple of concepts which kind of then inform our understanding of the EHT results. So this radio emission, both in this kind of a donut structure, and also the emission, the radio emitter I showed you of 3C273 earlier. We believe that all that radio emission is coming from incoherent synchrotron emission. And why do we believe that? There are several reasons. So synchrotron emission basically happens when, so this cartoon is showing that when you have fast moving charged particles around magnetic fields. So this is showing the helical path of one of the charged particles, and this charged particle then emits synchrotron photons. If the electron or the charged particle energy distribution is given by this equation, so this is number of electrons with some energy, and they fall with energy with respect with this form, so energy minus S, so this is the slope with which they fall. And when the energy distribution of the electrons is this way, this is known as the power law distribution, the photons that they emit also follow this power law distribution. So this is a spectrum that you get from synchrotron emission of charged particles. And so this slope here This is the slope which we call alpha in this case for the synchrotron photons. This alpha is related to this slope using this relation. So this is the electron spectral index, and this is the synchrotron emission spectral index. And this slope turns out to be, from theory, to be around 0.7 for an S of 2.4. So this is another observational constraint which has been obtained by several, like cosmic ray data, etc. tells us that the electrons have this kind of energy distribution, and the synchrotron photons have an alpha which is related by this and turns out to be 0.7. So we find that all the radio emission in the jets and even the torus-like structure which we saw for the EHT actually has a slope of around 0.7 or 0.75, which means that it is synchrotron emission. And so this particular spectrum, there are turns here because of several other physical effects, like there is a steepening of the spectrum at higher energies because the electrons lose energy faster when they are more energetic. So the rate of loss of energy is proportional to E square. So more energetic photons lose energy faster. And then this is the self-absorbed region, etc. So we can discuss that more if anybody is interested. So this is one fact which matches the radio emission observational data. The second fact that matches is that synchrotron emission is expected to be highly linearly polarized. So that comes from this cartoon used to show that this kind of linear polarization comes from the geometry of that radiation itself. So you can see that because the emission is emitted in a cone, it's very directional, and so it has a planar polarization, right? And so synchrotron theory in fact tells us that the maximum linear polarization that you should get from synchrotron sources is given by this relation, 3s plus 3 divided by 3s plus 7, s being the electron energy spectral index, and that is around 70%. And when we look at radio jets and even the EHT images, all the polarization, first of all, they're highly linearly polarized and it's never more than 70%. So because of these two pieces of evidence, we know that the radio emission that we see in the jets and the EHT images is synchrotron emission. So now another ingredient that must go into understanding the EHT results. So first of course I wanted to show this beautiful image of one of the AGN which has large jets. So this image is a composite of two images. So basically the yellow and blue light that you see is from the Hubble Space Telescope image, and this is an elliptical galaxy, very nice large elliptical galaxy. There is another small galaxy which is actually falling into this elliptical galaxy. So it's at some point it will be absorbed into this galaxy. And this pink emission that you see is radio emission, which is being launched from the black hole in this particular galaxy. So the extent of, as you can see, I mean, there are very interesting things here. The jets are also kind of, it's almost like smoke plumes, and the extent of these jets is much larger than the galaxy itself. So the galaxy is here, and the radio emission is much further beyond. This radio emission has been obtained using a particular radio telescope called the Very Large Array. So that is shown here. So this is a set of 27 telescopes, individual telescopes in the shape of a Y, and they basically use this configuration and Earth's rotation to then act like a circular radio telescope which has a diameter equal to the size, the largest baseline, which is called the baseline, the largest separation of antennas. So this is important because the EHT results, I think, as I will show you, depend a lot. I mean, radio interferometry is a very important integral part of the EHT image analysis. So that's why I wanted to spend a little time here. The GMRT, the telescope that NCRA operates, is also in the shape of a V. And it turns out the Y, that's a good configuration to get circular apertures. So the aperture synthesis is a big topic in itself, And but basically, a couple of things to remember are that the resolution, when you synthesize a telescope, the radio telescope is actually, it's not these individual ones, but all of this working together works as a single radio telescope, and that technique is called aperture synthesis. And the resolution, the how what kind of details can you see in the sky, that resolution then is given by this relation. This, of course, resolution relation is common to all telescopes, optical telescopes as well, that theta is equal to or similar to lambda by d. So in an optical telescope, the d will be the diameter of the optical telescope. In the case of radio interferometers, d is the longest baseline, so the largest separation between antennas. So because of this radio interferometry and aperture synthesis technique, we are actually able to do much more fantastical things in radio astronomy compared to optical astronomy. So for the first thing that we can do is we can use, the interferometry can end up resulting in much higher resolution than any other telescope can. So here I just wanted to show you these equations to also give you a sense of what the EHT actually sees. The Event Horizon Telescope, what is the data that it gets, and then how do you interpret, how do you go from that data to then saying that this is a black hole of so much mass or so much spin. So this is just to show that what we measure with radio interferometers is actually not directly the photons from the image, but a Fourier transform of the image brightness distribution. So what you measure in radio telescopes is what is known as the visibilities, and the visibilities are related to the actual intensity of the source in the sky with this using this relation, which is a Fourier transform. So the visibility itself is basically where you have your radio telescopes generating voltages as the source impinges on those telescopes, and then these voltages are multiplied and averaged, and then that turns out to be the Fourier transform of the original electromagnetic energy from the source. So this is a complicated topic. I just wanted to also flash this, there are several books on learning about interferometry and synthesis imaging in radio astronomy, and this is important for understanding the Event Horizon Telescope results. So another beautiful image, but also I have a purpose here. So here in this is another AGN. It's a radio galaxy called Picture A. So this is another composite image. There are two things plotted here. The red emission that you see is radio emission, and the blue emission that you see is now X-ray emission. So I had shown you earlier the Hubble Space Telescope emission and so optical emission. Here you are seeing X-ray emission, and this X-ray image was actually obtained by the Chandra X-ray Observatory. So what is there are several interesting things happening here. So this is the AGN basically, and the AGN is again launching jets. In this case, the jets are also seen in X-rays, not just at radio frequencies, but also in X-rays. And the jet seems to be going all the way here to this terminal point called a hotspot, and the core itself is the center, the AGN. The core itself is very bright in X-rays. The existence of this X-ray jet is in itself very puzzling, because unlike synchrotron photons, which have very long lifetimes, the photons, X-ray photons, have very short lifetimes. As I also showed you in the spectrum, for example, as you keep going to higher and higher energies, they radiate, they lose energy faster. So it's very odd that X-rays would actually survive this distance, which is usually tens of thousands of parsecs or light years. So it's very interesting that the X-rays actually survive this, and in fact it's believed that the X-ray emission is somehow the particles are getting energy not just from the AGN but all along the way. So this is another very interesting field of AGN jet physics that is being pursued. Also, this has now become even more interesting after the discovery of neutrinos from active galactic nuclei, or also gamma ray emission, etc. So that so multi-messenger astronomy is now informing us about these jets themselves. But in this case, how it relates to the EHT is from the center itself, what is called the core or the nucleus. So this is the bottom panel is actually a cartoon. It's not an image, and this is showing an accretion disk. It's showing a black hole, and maybe this you could imagine all this yellow emission or the red emission is actually X-rays. So the X-rays from the nuclei usually come from the inner parts of the accretion disk or from the poles of the spinning black holes. And the poles of the spinning black hole have this particular region which is emitting very brightly in X-rays, which is called the corona. A corona is like the geometry of the corona is still is still being debated, but it's some kind of compact feature just above the black hole and accretion disk system. So this X-ray emission is what's dominating this slide that you see here. So it's not from the jet so much; it's actually from the accretion disk and the corona. Okay, and then now the last piece, which needs also to be described to actually explain the EHT results, especially from M87. So this another discovery that was made by X-ray telescopes, in particular the Chandra X-ray observatory, was that when Chandra looked at galaxy clusters, it found that, so this diffuse emission that you see is X-ray emission, and it found that this X-ray emission seemed to have a lot of holes in it. Okay, so these are called X-ray cavities. And there are other interesting results as well, like what is called the cooling flow problem, which I can of course talk about separately. This is kind of an indication that somehow or rather this is an indication of that. When you look at this image now, you also kind of get the radio information from this this particular, there's an AGN here actually, I should say that. There's an AGN here. And if you take a look at the radio emission from this AGN, which is shown here now in these red contours, this red emission or radio emission fills these cavities. So whatever was like empty in the X-rays is actually filled by the radioplasma. So this is telling many things. It's telling first thing that the AGN itself is actually able to influence material outside of its own galaxy. Okay, so it's actually influencing the evolution of even galaxy clusters. It influences the evolution of the galaxy itself and also galaxy clusters. So that's one thing, and that's a phenomenon called AGN feedback. But importantly, this coincidence of the radio emission with these X-ray cavities is also the way to find how much power is there in the jet itself. So that is what is known as the jet mechanical power. How much power is there in the jet is actually estimated using this simple formula, which is pressure into volume. So you take the volume of this cavity, which is something that is observed, and the pressure of the X-ray gas, which is also something that you can get from the X-ray data modeling, and that PV times gives you the power of the jet. So this is the way to get jet mechanical power based on X-ray cavities. Now the final thing, so I'm kind of giving you lots of ingredients and then I'll just try to put everything together. The final thing that is relevant is the question about how are jets formed. This is an open question, and there's a lot of work being done about the formation of jets, and this is a cartoon to show one of the mechanisms which have been proposed. So this cartoon is showing an accretion disk in a black hole, which is threaded by some weak magnetic field lines, and then as this black hole and accretion disk rotate, these field lines kind of get wrapped around like this, and then whatever material is ejected from this black hole accretion disk system is kind of collimated through these field lines. So, so that's the cartoon, and the two most favored jet emission mechanisms in the literature, they've been around for a long time. It's only now that we're actually able to test these. So, this work by Blanford and Znayak in 1977, they suggested that to get these very large jets, I already showed you how large these jets are. Like they are much larger than the galaxies in which they form, and they have suggested that the energy of these jets, and it's actually coming from extraction of the angular momentum of a spinning black hole. So actually, the jet is powered by the energy from the spinning black hole, and so this is known as the Blanford-Znayak mechanism. And the power that is extracted is proportional to the magnetic field strength around the black hole and the angular velocity, the velocity with which the black hole is rotating. Another emission mechanism which had been put forth by Blanford and Payne was that instead of the black hole, it was the rotating accretion disk which was powering these outflows. So the energy and angular momentum were extracted magnetocentrifugally from these accretion disks. So these were two mechanisms which have been, in the literature, and there has been a lot of debate like which one works. Maybe some work for one type of jets and some for the others. And EHT, of course, is telling us very interesting things about these two mechanisms. So now I finally come to the EHT itself. So what is EHT? EHT is very long baseline interferometric, the technique using millimeter waves. That's what EHT is. So how does VLBI work? So so this is a cartoon to show how VLBI works. I showed you in the beginning you had the very large array which had this Y-shaped array of antennas, and in that kind of a telescope is called a connected interferometer. So that means that the antennas are actually connected to each other by optical fibers, and the signals are kind of in real time obtained from different telescopes and correlated or multiplied, averaged in one central location, and that happens in real time. VLBI, you can use two radio telescopes which are not connected to each other, so they can be very, very far away, as far as the diameter of the Earth. Actually, some of them can be even done if you have one telescope in space. That's called space VLBI, and that has been actually done. So the only condition that you have to meet is that both these telescopes have to be observing that same source at the same time, so that the wavefronts from this particular source are detected by both these telescopes simultaneously. And then you have to record the data separately in these two telescopes on magnetic tapes. The important requirement is that this data has to be time stamped with very high accuracy, time accuracy. So atomic clocks are used, for example, the hydrogen maser, etc. And why is that needed? Because you want to make sure when you combine the signals, when you do the interferometry of these two signals, that you have the exact time when a particular wavefront was received. So you need to have a very highly time accurate, time clock at these two telescopes, and then later you play these tapes back and then correlate the data with accurate timestamps. So that's VLBI. So the nice thing about VLBI, I mean, the fact that you can go to very large distances means you're arbitrarily increasing the longest separation between antennas. So you're already increasing the resolution of your telescope. So that's why VLBI is very important. So this set of equations is, I think I don't have to dwell on this. I just wanted to say that when you do VLBI, you basically go to very high resolutions, and then you are able to start imaging the black hole and the accretion disk and the jet when it is launched. So when you come to that regime, that is where interesting physics is happening, and all laws of special theory of relativity and general relativity, everything is now important in that particular regime. And special theory of relativity, for example, will tell you that some very counterintuitive phenomenon start taking place, And so I've given some relations, you don't have to worry about these relations, but basically whatever luminosity you observe is actually not what is, or rather whatever power you see is not what is actually intrinsically emitted, but it is actually multiplied by a Doppler factor, which is given by this relation, Doppler factor, which has gamma, which is the Lorentz factor. Lorentz factor has a beta, which is speed with respect to speed of light. Theta is the angle, angle to line of sight. So basically, any emission which is moving at speeds very close to speed of light and towards us will automatically be Doppler boosted and look much brighter to us than it is in the frame of the source itself. So this is the Doppler beaming effect. So this becomes also important to understand what we see in the EHT results. The other thing is that you start seeing jets, even though in the initial cartoon I showed you these two jets, bipolar outflows, they seem to be symmetric as they are launched. But when you look at VLBI images of these sources, you always see only a one-sided jet. And that is only because this is a kind of an optical illusion in some sense. This is happening because the jet which is coming towards us is Doppler boosted, and the jet which is going away from us is actually Doppler deboosted. So you don't see it. But of course both the jets are there. It's just like it appears like this. So this will help you also understand why what these images are. So the power of VLBI I think is kind of captured very well in this slide. So on the top is a radio image of MET7. Okay, Messier 87. This jet is seen in the optical frequencies also. You've seen that is the first image I showed you from Curtis. And then you have all this radio plasma here, etc. Now this is with a very large array. This, if you just look at this, what is called the core, the nucleus of it with VLBI. So this is very long baseline array, which is a set of telescopes which does VLBI. Then you see another kind of core and jet structure, but it's one-sided, right? It's actually one-sided even here. There's a little bit of dim emission here, you don't see it very well. But this, when you go to VLBI scales, it's definitely one-sided. Then you go at this, look at this telescope with another VLBI array, which is the giant, global millimeter VLBI array, GMVA. And then again you see a core and jet, and this time the jet also starts looking very interesting. You see the jet has these bright edges. It seems to be empty, there is less brightness in the center, etc. So that also is saying something interesting about the magnetic field configuration in this jet. Then you'll go to even higher resolution with the Event Horizon Telescope, and then you are able to actually get this image of the black hole in this very region. And what are we doing with this? Like, so basically if you look at the frequencies, so I told you, right, that the resolution is lambda by d. So you can either keep increasing d and get higher resolution, or keep decreasing lambda. So this is what's happening here. So you go from 43 gigahertz to 86 gigahertz to 230 gigahertz, which is what that frequency at which EHT operates. So EHT is basically a millimeter wave VLBI array. And so this is a cartoon to show the different telescopes which were involved in creating the Event Horizon Telescope. And because you're operating already at 230 gigahertz, which is 1.3 millimeter. So to give you a sense of what this is, the GMRT, for example, the observations are several centimeters, several tens of centimeters. And so this is 1.3 millimeter. So at this frequency, the resolution of this particular telescope is already in microarcseconds. Okay, and that apparently turns out to be enough to see the structures in MET7, both MET7 and Sagittarius A star. Sagittarius A star is the radio source in the center of our own galaxy. Now, so again, I had introduced you to aperture synthesis, so I just wanted to point out what goes into the modeling of the EHT data. So on the top is basically showing, these are called UV tracks. I think details are not important. I did tell you what UV was. That is the spatial frequency components in the Fourier domain, and these are tracks made by these telescopes as Earth rotates. And so this now, all these tracks then add up. It's almost like this whole thing is working as a single telescope of whatever large diameter. Then you get the visibility data from there, which is what is shown here. This is visibility data. So this is already the Fourier transform data from these different telescope baselines, and then this data is what's modeled to get the final, to infer what the EHT is showing. So I will come to that later. So this is a little bit technical because I did want to tell you what EHT does. So what does EHT, how do you go from that donut-like image to actually inferring something about the black hole? So there are a couple of steps, and so this is a lot of text, but let me just try to make it as simple as I can. You start by running general relativistic magnetohydrodynamic simulations, GRMHT. So basically you start with, you have a hot plasma which is turbulent and magnetized, and this plasma is orbiting around a black hole, which is a Kharb black hole, which is it's a rotating black hole. A rotating black hole has some plasma around it, which is turbulent, hot and magnetized. And then you run these simulations to see how this evolves. The ingredients that go into this are two ingredients. One is the spin of the black hole itself, the black hole, how fast it's spinning, and the spin parameter is given by this relation, where J is the spin angular momentum, C is the speed of light, G is the gravitational constant, M is the mass of the black hole. The second ingredient in these simulations is what is known as a magnetic flux, and magnetic flux is given by this relation, where M dot now is the accretion rate, like how much mass per unit time falls into the black hole, right? That's the accretion rate. And square of the gravitational radius into speed of light. Gravitational radius itself is a very fundamental unit, length scale associated with black holes, and it's given by this relation, G m by c square. So gravitational constant by mass of the black hole divided by speed of light square. So these two ingredients, the spin and the magnetic flux, are the two inputs that go into the GRMHT simulations, and then you evolve this to see what you get. This magnetic flux is, we know this is non-zero because magnetic fields are usually trapped in the accretion flow around black holes, and they are sustained by currents in the surrounding plasma. So you already start with some kind of a weak seed magnetic field, and then they produce currents, and then the currents then also produce magnetic fields, so magnetic fields get influenced that way. So this is the basic premise of a magnetohydrodynamic plasma, so MHD physics. So with these ingredients you run these simulations, and so for example in the case of M87, these simulations were able to produce a powerful jet in the case of M87. Given there are some basic inputs that go into it, including the black hole mass and distance to M87. So 4 different types of codes were run, and there were 400 different physical scenarios were generated from these simulations. And these simulations basically helped create what is known as a simulation library. Like different inputs and the different outputs that come out of these simulations, right? How does plasma evolve around a black hole? So you have so many physical scenarios. Then from there you use what is known as a general relativistic ray tracing technique, or GRRT code. It's a radiative transfer code, and create synthetic images. So from simulations you do the GRRT to get synthetic images. I'll tell you what this GRRT does actually. So 3 GRRT codes were used, and then they created some 60,000 images, synthetic images. Okay, so what are these? What is this synthetic images? How are they made? So the ingredients that go over there. So you have to assume the accretion disk is a certain kind. So two types of accretion disks were assumed. One is known as a standard and normal evolution disk. The theoretical work is done, for example, in Ramesh Narayan's paper. They have a certain magnetic flux associated with that type of disk, type of accretion disk. And then you could have another disk which is known as a magnetically arrested disk, MAD, which is also this particular paper. The other inputs are these accretion disks rotating in the same sense as the black hole. So if they are they're moving the same way as the black hole, then the spin parameter is taken to be 0 or positive. If they're moving in the opposite direction, then the spin parameter is taken to be negative. The images themselves, what I mentioned about the GRRT, that assumes something about the plasma now. So it assumes, or rather it requires the magnetic field, it requires how this plasma is moving, the velocity fluid, what is the density of the fluid, what are the emission and absorption coefficients, what is the inclination of this accretion disk with respect to us, what is the black hole mass, what is the distance to the observer. The plasma itself is assumed to be ionized hydrogen, and the ions, which means electrons and ions are assumed to be non-relativistic and electrons are assumed to be relativistic. So these are moving to speeds close to speed of light and these are not, and they both have different what are known as brightness temperatures. So this goes into the second part of it. From simulations to images, this information goes into it, and once you have a synthetic image, and I told you there are some 60,000 images that were generated for MET7, you then go from images to actually create visibilities. Okay, so I showed you how visibilities were obtained in the previous slides, and those visibilities are then compared with the observed visibilities, right? So let me just go back very quickly here. This one. So these are the observed visibilities, and now what you see this as this dashed line here is actually from the synthetic images. That is the model visibilities, and then you try to see which matches your data. So that is how you zero in on the model that fits. So I did tell you about the jet power in the previous slides. So they did use this as another constraint to decide from this whole simulation library and this whole image library, synthetic image library, what model works best. So one of the inputs that go into this is the jet mechanical power, and so this is an X-ray image of MET7 which shows an X-ray jet. It also shows cavities, and from these jet cavities some kind of jet power has been estimated using P into V, and that's around 10 to the 43 ergs per second. And the second input observational constraint is the X-ray luminosity coming from the nucleus. So this is an X-ray image, the same X-ray image actually, and the luminosity from this nucleus was obtained, and that is around 4.4 10 to the 40 ergs per second for MET7. Also the emission mechanism was synchrotron self-compton. I mean, that is not important right now, but basically these, apart from going from simulations to synthetic images to then visibilities, and modeling the model visibilities then being compared to the observed visibilities, you also have these additional observational constraints. You have to have the jet power should not exceed let's say 10 to the 42 43 ergs per second, and the X-ray luminosity which will come from the top of this corona, which is also a natural result of those simulations. The simulations kind of produce this coronal region. So that luminosity in the X-ray should not exceed what you actually see. So these observational data then constrain also the models further. So this is done just to show you the kind of things that were done to finally deduce about MET7. So these, for example, these are the inputs that went into it. So you had a whole set of sane models, MAD models, which had certain spin parameters, a range of spin parameters. Then another factor which I'm not really going to talk about, but basically related to the temperatures of the ions and electrons. And then you match this to see if these models also manage to explain the X-ray luminosity and the jet power. And then you write if this model works, or this model, which set of models actually works to explain everything. So based on this kind of analysis, it was concluded for MET7 that there is first of all a mad accretion disk. So the disk is magnetically arrested, and it's a highly magnetized accretion disk. It is moving, it's around a rotating black hole. So all black holes which are not rotating are completely ruled out from the EHT data based on this kind of analysis. And the third thing is that the jets which are launched in MET7 are from the Blandford-Snipe mechanism. So this is another thing that comes from simulations, and it's kind of, on a very strong footing that the jets are actually coming from the Blandford-Snipe mechanism. And if you remember, I had also shown you Blandford-Payne, and there are also many other jet emission mechanisms, jet production mechanisms, which don't seem to work. So now this is just the second last slide that I wanted to show you, but like all the results that have come from EHT for MET7 and Sagittarius A star. So these are the two black holes, one from MET7, one from Sagittarius A star. The diameters of these rings is around 40 microarc second for MET7 and 50 microarc second for Sagittarius A star. The fact that they are so similar is because if this black hole is much more massive but more distant, and this is a less massive black hole but closer. So somehow those distances are working out to give you the comparable ring diameter. Sagittarius A star, if you have been following EHT results, the announcement came much later. It actually came only a couple of months ago, and the announcement for MET7 came in 2019. Even though the data were actually acquired at the same time in 2017. And the reason this took so long is that Sagittarius A star, there's a lot of scattering happening due to interstellar electrons in the galactic center, and this is changing the radio flux density on our timescales of hours. Okay, so it is very difficult to actually arrive at this image for Sagittarius A star. So I have also written here the Sagittarius A star, the additional constraining data which I told you for MET7, which was the jet power and the X-ray luminosity from the core. There is no jet in Sagittarius A star, so the constraining data in this case was a particular feature that is observed in Sagittarius A star called a sub-millimeter bump. So we don't have to go into the details, but it turns out that the mad accretion disk also is present in Sagittarius A star. So, and the black hole is also rotating. So mad accretion disks are present in both of them, and both of them have rotating black holes. The masses of black holes are listed here. And the final thing, again, I think these equations are not particularly important. The important thing is to note that both these black holes, the accretion rates are very, very low. So these are called Eddington scale accretion rates, which are 10 to the minus 5 for MET7, 10 to the minus 9 for Sagittarius A star. So both these AGN are kind of starving black holes. There's not much accretion happening into them, especially Sagittarius A star. And even so, the mystery is, of course, that even though they're in the middle of a galaxy, there's a lot of star and gas available, but somehow that is not being funneled into the black hole. So that is that's one question. And of course, like I mentioned, the jets in MET7 seem to be launched from the Blandford-Snipe mechanism. I will just end the talk now by saying that EHT has shown that the general relativity predictions seem to be working, in these two very different sources which span 3 orders of magnitude in the black hole masses. The predictions have been borne out by the observations. So I think with that I can stop, and happy to take questions.
Yeah, thanks, Preeti. We have questions from audience. You can unmute and ask. Anybody? Uh, by the time somebody asks, I will just to keep going. I will ask one question that you have shown in the last slide. The two photographs of the EHT they have released of two black holes. We see that there are some concentration of the photons or whatever it is in for example, we have three such lobes in our Sagittarius black hole, and
Yes.
we have a M87 semicircular two lobes, and partially it is very dim. So
Yes.
you said that all these are actually we are taking because these galactic jets and all, and they are trying to make a composite thing about the images. So
Yes.
can you just explain a bit more because
Yeah. So, so I'm assuming that you're talking about these bright
Yeah,
features,
yeah,
etc.,
yeah,
right?
yeah, yeah.
Yes. Yeah. So actually, that's a good point because I did introduce my whole purpose of introducing the concept of Doppler boosting was actually to explain this, but then I completely forgot. So in M87, this ring is brighter towards the south compared to the north, and that is because of this material actually is coming towards us, and so that emission is Doppler enhanced because of Doppler. So basically, the material is moving almost close to speed of light, and the Doppler factor then comes into play to explain the observed brightness. So this emission is actually coming towards us, and that emission to the north is going away from us. So this even tells you about how this actually the accretion seems to be in the clockwise manner in the sky for M87. For Sagittarius A star, apparently these bright features don't mean that much yet, because different groups, when they created this image, found that these bright spots were in different locations for them. The EHT collaboration doesn't want to place any significance on these bright knots. Because I think they probably need much more data, and because Sagittarius A is so variable, so you can't believe what you see here. So you can't say much about this brightness actually.
Okay. Anybody else? Any questions?
I think must have been too technical. I can completely
No,
imagine.
it was fine. It was fine. I liked it, and I hope everybody liked it. You have explained all the equations and the graphs, whichever you have brought in. So that was
Yes.
quite good. Anybody else? Anybody wants to ask anything? You can unmute and ask. Okay, so if there is no questions, I thank Dr. Preeti for having given us her time and given us an explanation of all the images, because this is one of the topics which people are actually speaking about now, and a lot of people want to know about it. And I am sure that many people are watching this in YouTube and FB, and so maybe in future, if means others can also contact her directly. If you have any questions or specific thing, you can write to her. Her email address is there in NCRA website. I thank Preeti for giving me.
Thank you, Jen. Thank you so much. I look forward to questions.
Yeah.
Thank you.
Renil?